Welcome to the deep dive. It's funny. When things get tough down here, we humans, we always seem to look up, don't we? Dreaming about other worlds, wondering if maybe, just maybe, there's life out there.
It's a really deep-seated thing, that curiosity, asking if we're alone or if someone else is out there looking back.
Exactly. And today, we're really diving into that. We're looking at how science, especially now, is trying to answer that huge question. Could life actually exist somewhere else?
And the starting point, scientifically speaking, is always the basics. What does life, at least life as we understand it, actually need?
Right. The essentials.
Well, number one is liquid water. That seems pretty non-negotiable based on life here.
Yeah.
And crucially, you need a stable atmosphere.
Ah, the atmosphere. Not just for breathing, I guess.
No, not at all. It's vital for keeping that water liquid. It provides pressure, regulates temperature, basically stops it all from just, vanishing into space or freezing over instantly.
Okay, so water and a decent atmospheric blanket. Got it.
Well,
Which brings us to TRAPPIST-1. That system generated a lot of buzz a few years back, didn't it?
oh, absolutely. TRAPPIST-1. It's a red dwarf star, relatively close, about 40 light years away. And the big news was discovering it had 7 rocky planets orbiting it. 7.
7, wow. And several looked promising.
That was the really exciting part. 3, maybe even 4 of them seemed to be in the habitable zone, the region where temperatures might allow for liquid water. TRAPPIST-1 in particular looked like a prime candidate early on. Similar in size to Earth, right distance, potentially water-friendly.
It sounds almost perfect on paper. But science moves fast, and new data changes things. So our mission today is to unpack what the James Webb Space Telescope, the JWST, found when it looked at TRAPPIST-1 pent. What does this new data tell us about habitability there, and what does it mean for the bigger search?
Exactly. We're going straight to the findings. Because for a while, TRAPPIST-1 really was the poster child. Earth-sized, in that habitable zone. It ticked the initial boxes. People genuinely thought this could be it. An Earth cousin.
So the hope was high. Then JWST, with its incredible capabilities, finally took a look. What did it actually see?
Okay, so the observation happened in November 2022. JWST used its near-spec prism instrument. Think of it like a superpowered prism that splits starlight to find chemical fingerprints. It watched TRAPPIST-1D pass in front of its star twice. That's called a transit. As starlight filters through any potential atmosphere, gases leave specific signatures.
And a big international team analyzed this data.
Yep, researchers from Canada, the UK, France, the US, they published in the Astrophysical Journal. The title itself tells you a lot.
Yeah.
Strict limits on potential secondary atmospheres on the temperate rocky exo-Earth TRAPPIST-1 pent.
Strict limits. That doesn't sound overly optimistic. So what did the data, the spectrum, actually show? Was it what they hoped for?
Well, simply put, the transmission spectrum was flat, completely flat.
Flat.
Meaning no dips, no bumps, no absorption lines. Essentially no detectable signs of gases like water vapor, carbon dioxide, or methane, the kind of stuff you'd expect in a substantial atmosphere.
Okay.
It's basically the opposite of what you'd hope to find if you're looking for an Earth-like world. It was quite definitive.
Wow. That must have been, well, a letdown after all the anticipation. It highlights that science isn't always about finding what you expect, is it?
Absolutely not. Discovery often means ruling things out, and the researchers were very clear about what this meant.
How did they put it?
Caroline Piela-Goraeb, one of the lead authors, said it quite directly. Something like, while JWST lets us explore these planets like never before, we can now rule out TRAPPIST-1D as an Earth twin or cousin.
Rule it out. Pretty blunt. So explain why that flat spectrum, that lack of atmospheric signature, is such a big deal for habitability.
Okay, so a flat spectrum points to a few possibilities, none of them great for life as we know it. Either the atmosphere is incredibly thin, maybe like Mars.
Right, not much protection there.
Or it could have really thick clouds, but way up high, blocking any view of what's below. Think Venus, but maybe different composition.
Also not very welcoming.
Or the simplest explanation might be, there's just no significant atmosphere there at all. The bottom line is, this flat spectrum rules out the kind of thick, protective atmospheres, whether hydrogen-rich or Venus-like, that you'd need to keep surface water stable.
So without that atmospheric blanket, any water would just disappear.
Pretty much. It would either freeze or boil away into the vacuum of space. So, yeah, highly unlikely to have surface water.
Okay, so TRAPPIST-1D seems like a dead end for now. What's the likely reason? Why would it lose its atmosphere or never have a thick one to begin with?
The finger usually points towards the star itself. TRAPPIST-1 is a red dwarf.
And red dwarfs are common, right? The most common type of star.
Exactly. They're everywhere in the galaxy, and we know they often have rocky planets,
Yeah.
but they're also known for being quite violent, especially when they're young.
Violent how?
They flare a lot. TRAPPIST-1 flares frequently, like every few days. And it also has these massive super flares, maybe 4 to 6 times a year. These are way, way more powerful than anything our sun throws at us.
That sounds intense, like living next to a cosmic fire hose. How does that affect a nearby planet?
Well, all that intense radiation, those bursts of X-rays and charged particles and things called coronal mass dejections, huge blobs of plasma, they can literally blast a planet's atmosphere away over time.
Right.
Especially for planets orbiting close in, like TRAPPIST-1b.
Let's just strip it right off.
Yeah, atmospheric stripping. It's a major concern for planets around red dwarfs. Now, there is some debate. Could a strong magnetic field protect a planet? Maybe. But many scientists think the constant, intense bombardment from flares and CMEs makes it incredibly hard for these close-in planets to hang on to any substantial atmosphere long-term.
So it's constant battle against the star's fury. Bjorn Benneke, another author on the paper, mentioned something about this being just the start, right? Using Webb to figure out where that line is.
Exactly. He said we're just getting started using Webb to see where the line lies between planets that can keep their atmospheres and those that cannot. It's a huge question in exoplanet science right now.
Okay, so if TRAPPIST-1 is likely out because it's too close to this angry star, what about its siblings, the other planets in the system? Is there still hope further out?
Yes. That's the crucial next step. While one deal looks pretty inhospitable, the focus shifts outwards to TRAPPIST-1, F, G, and maybe even H.
And why might they be different? Just because they're further away?
Precisely. They orbit farther out. So the star's radiation, the flares, all that nasty stuff, it's weaker by the time it reaches them. Less intense bombardment.
Meaning they might have had a better chance of holding on to their atmospheres and any water they started with?
That's the hope. They might have been able to retain thicker atmospheres and potentially keep liquid water, or at least water ice that could melt under the right conditions.
But I guess studying planets further out, which are colder, is harder for JWST.
It is definitely harder, yes. Colder planets emit less infrared light, which is what JWST primarily sees. Detecting faint atmospheric signals is tougher.
Still, there's some optimism based on models.
Yes. Theoretical models suggest these outer planets could have held on to volatiles, things like water and gases, even if they didn't start with a huge amount. Maybe just a few Earth oceans worth initially.
So even starting with less, their location might have saved them?
Potentially. As Ryan McDonald, another co-author, put it, he said something like, "Thanks to Webb, we know TRAPPIST-1 day is far from hospitable, but the outer planets may still surprise us."
A cautious optimism, then. And what about that tiny possibility for one day the Terminator clouds? Is that still on the table?
Well, it's a very slim possibility. Some models suggest clouds could form permanently on the day-night boundary, the Terminator, which might flatten the spectrum. But even if that's true, it still wouldn't make it an Earth-like world. Far from it.
Okay, so zooming out, what does this finding about TRAPPIST-1 and day really tell us in the grand scheme of things?
I think every time a promising candidate like this turns out to be, well, not Earth 2.0, it really hammers home how potentially rare Earth might be. It refines our search. It tells us maybe we need to look more closely at different types of stars or different types of planets. It forces us to understand the specific conditions needed for habitability better.
And it connects back to that human element we started with, doesn't it? The search isn't just cold science. It's driven by this deep hope, this desire to know if we're alone.
Absolutely. It's about finding our place in the cosmos, understanding the context of our own existence.
So TRAPPIST-1 wasn't the answer, at least not the one we hoped for. But JWST is really just getting started. The story of TRAPPIST-1 isn't over, and neither is the broader search.
Not by a long shot. There are still those outer planets to investigate, and countless other star systems JWST will turn its gaze towards.
So just to quickly recap what we've covered.
Sure. We talked about the initial excitement for TRAPPIST-1, this seemingly Earth-sized world in the habitable zone.
Then the JWST observations came in, revealing that flat spectrum, a big disappointment for finding an atmosphere.
Right. And we discussed how the star itself, a volatile red dwarf, is the likely reason, constantly battering its inner planets.
But there's still hope, shifting focus to the outer planets in the system E, F, G, and H, which might have fared better.
Exactly. The search continues there.
And maybe the most fascinating thing to leave you, the listener, with is this. Even when a planet like TRAPPIST-2 doesn't pan out, it teaches us something vital. It deepens our appreciation for the sheer complexity, maybe even the fragility, of the conditions that allow life to exist here on Earth. It makes our own world seem even more extraordinary, doesn't it?
It really does. The search isn't just about finding another Earth. It's about understanding the intricate, maybe improbable cosmic dance that allowed our Earth to happen at all.